This is a dual triplexer. It splits the incoming signal into 3 different frequency ranges, loads 2 of them with 50 ohms and send the one in the middle to operational amplifiers that are not loaded at all. So those amplifiers, they see the impedance of the source, and that minimizes noise, of course. Here's the schematic diagram. This unit is intended to use with the Schottky barrier mixers. They present a 50 ohm impedance roughly. Frequencies above 5 megahertz or something, at least 10 megahertz, where the RF might occur. We'll see 47 ohms through this 3.3 nanofarad capacitor. Very high frequencies are blocked by this inductor and the following 3.3 nanofarad capacitor. Cutoff is around 1 megahertz. Then this is a big coil. It presents a 47 ohm load to DC and frequencies below about 15 hertz. Then this capacitor couples what is above 15 hertz into this, which is a hybrid. It isolates the 2 amplifiers. If I remove this and connect the amplifiers, the plus inputs in parallel, all the noise that comes out is perfectly correlated. So I cannot gain anything by doing correlation spectra. They have to be isolated because the equivalent noise input current is a real current, and if we connect the 2 plus inputs together, they will see the same current, the same voltage developed over the input impedance. So all the noise will be fully correlated. And then there are the 2 outputs intended to go to the 2 channels of a sound card, the 2 I channels, and then an identical arrangement for the 2 Q channels. Here is the arrangement I used in a previous video, and now I'm going to do something very similar. Local oscillator, an hybrid to split it, and then one directly into a mixer and the other delayed by a quarter wave, so it is a 90-degree phase shifted. And then there are 2 mixers, plus 27 dBm Minicircuits. The signal into the mixers come from a hybrid splitter, and the main signal is from a local oscillator, the test object, so to say. There is a 20 dB coupler where I can inject the signal from a signal generator. And then a low-pass filter. I have replaced it with another filter with slightly lower losses. And then there is a 20 dB coupler to allow the spectrum analyzer to see the signals I'm sending into the hybrid splitter and further into the mixers. So up to this point, this is a conventional direct conversion receiver. This block. And then I'm generating a suitable test signal for it from the one oscillator that I want to test, and a reference signal that I can inject. What I'm doing now is to remove these low-pass filters and the step-up transformers and put this triplexer with amplifiers in it between the mixers and the UADC4, the AD converter designed for use with direct conversion radios. It operates like a sound card and uses normal sound drive routines. Here are the signals that I'm sending into this receiver. The strong signal is at plus 0.3 dBm and the weaker signal is minus 49.7 or so. Maybe I should increase it a little. No. Well, the injected signal is now 50 decibels below the carrier. And looking at the Linrad screen, I have placed the signal very close to the edge because I have added this notch filter, which is 50 kilohertz below the signal frequency. That's to make sure that the signal from this oscillator doesn't have any noise at this frequency where I'm looking, because I'm looking for the properties of this test system. And the local oscillator should be far better, so I have no filtering on that. Anyway, what I have to do now is to calibrate properly, and I want to show minus 50 here. So now it shows minus 50 on this reference signal, which means that the carrier is at 0. And I switch off this calibration signal, and here is the noise floor. Minus 141.3. And then I look at the correlation noise. It is the noise that is common to the two audio channels is 5.5 dB below minus 141.2. Means 146.6. And the bandwidth is accurately set to 1 kilohertz. It means that the noise that I see, that I think comes from the Schottky mixers, is at minus 176.6. With room temperature dummy loads on the input of the triplexer, the noise floor I can read out. It was 141 before, and now it is 142.8. That's not a big difference, but looking at the correlation, it is now 13 dB, because these two room temperature resistors have their own thermal noise, and that doesn't contribute to the correlation spectrum. So I'm actually looking at 142.8 plus 14, that is 157 something, and that means 187 dBc per hertz. That's the limit of the test system I have at the moment. These things are non-trivial. Here is an artifact of some kind, a little hump here, more visible in the correlation spectrum than in the direct spectrum, but we can see it very clearly in the waterfall. And I find it's some kind of interference. I move this box here. I don't know exactly from where this interference comes, but now it is very strong. And other things also come up. So I will have to investigate this. This is a magnetic field probe, some ferrite rods with some wire around it, and then a coaxial cable, and I connect it to this triplexer, and I look at the screen and placing it here, and you see horrible interference, and the box is not tight enough at this low frequency to screen this out. And I move this here, and you see if I go behind this screen, it goes down again. So it's generated by this, I don't know how to pronounce that, AOC perhaps. So this screen is generating a lot of fairly low frequency interference. I will look on the oscilloscope. This is what it looks like. Seems to be something like 250 kilohertz and 100 millivolts per division, so it's a strong signal. And if I switch the screen off, like that, then the pattern changes. The power supply is still running, but much less. Well, this is another screen, and I have connected that magnetic probe to the oscilloscope in the same settings as before. And this is a little bit less magnetic interference, but the difference is not very large. So it seems I have to try to learn how to screen this, or maybe move it more far away. I now use this coil connected to this signal or tone generator and search where is the box most sensitive. Looking at the S meter here. And that's here, and it's on top of the op-amps, I think. Anyway, what I can do, I keep it on the same place and insert 1 millimeter of aluminium in between. And the level went down by about 20 decibels. So I removed the aluminium, and you can see it makes a big difference. So I will make some aluminium shield to put on top of this box. The triplexer is now inside 1.5 millimeter aluminium. What I see on the screen, the normal noise floor is minus 141.3 or 0.4. I can take it once more. Minus 141.6 this time. (141). Well, let's say 141.6. The bandwidth is 1 kilohertz, and the correlated part of the spectrum is 7 and 7.4 dB down. So this sums up to something like minus 179 or 178 dBc per hertz. I switch on the test signal, and it comes at minus 50, I hope, minus 50, and the signal is set 50 decibels below the strong signal here. Plus 0.3, and well, it should be a little bit stronger. Things drift with temperature. So this doesn't make a big difference. It's a couple of tenths of a dB. So I have gained half a dB in the measurement. I have a 3 dB attenuator on the local oscillator to fit the 23 dBm mixers. I will remove it and see what difference that makes. And to that end I have calibrated properly now, -50, and then I have to wait for the noise floor and Alt-Z to clear the correlation spectrum. And I have to wait a little while. So what I see now is -141.79 and 7.8. That sums up to -179.6 dBc per Hertz. And now I will remove that 3 dB attenuator and recalibrate. So I didn't change calibration yet, but the first thing I can see is that the signal level has increased by almost precisely 1 decibel by doubling the LO power. So I have changed the calibration figure, and now I read 49.99 minus and switch off the test signal. And probably the noise floor has increased by about 1 dB. I don't know, and I have to clear the correlation summation. And here I have lost a significant amount. And the noise floor is now -142.14 and correlation 5.6. And that sums up to -177.7 dBc per Hertz. So too much LO power seems to increase the noise generated by the mixer. Now the attenuation on the LO is 6 decibels, and I lost then 1.4 dB. That's a little bit surprising, I think. Anyway, I will calibrate for this. So now the scale is correct with respect to the carrier, and I switch off the test tone. And there is less correlated noise. And what happened to the noise floor? 141.6 and 9.3. That sums up to -180.9 dBc per Hertz. Quite interesting, I think. I've changed the vertical scale, and I look here. It's clear there is a notch. It is this notch that is about 30 decibels deep. So what I see here is the properties of the receiver, I mean the Schottky mixers. And at the other end, I don't see anything like that. Here I see the dominating part here is the noise of the oscillator. I mean this box. So the noise floor here minus 141.6 minus 10 dB, 151.6 plus 30 for the bandwidth, 181.6.